In this section, we're going to talk about the different kinds of intermolecular forces, the forces that hold condensed states, meaning liquids and solids, together. So the strength of the intermolecular forces within a compound depends on the structure of those particles. And the state of matter at a particular temperature will depend on how strong the intermolecular forces are. So if we have strong forces holding those particles together, we have to get to higher temperatures in order for that substance to melt or to boil. Whereas with weak forces, they will melt and boil at lower temperatures. The intermolecular forces all come from interactions between charges. These charges can be partial charges. They can also be temporary charges. But it's all about positive and negative attracting each other. This is Coulomb's law. And the important part here is the Q1, Q2, and R. We're not going to do any calculations with this, but understanding this relationship helps us to understand some of the trends in intermolecular forces. So Q1 and Q2 are going to be the charges on the particles being attracted. So if those charges are bigger, like if we have +2 and -2, that product is -4, compared to +1 and -1, the product is -1. That's going to make the energy or the force of attraction 4 times larger for +2 charges. R here is the distance between the particles, and the larger the distance between the particles, the less attraction there is. So this is like putting paper behind a magnet on the fridge. And you put another piece of paper and another piece of paper, and eventually you've got so many pieces of paper there, the magnet can't hold them up anymore. And you've just increased that distance between the fridge and the magnet a little bit, but it affects how tightly the magnet can hold to the refrigerator. So bonding forces are different than intermolecular forces. So here we have a water molecule. This is a covalent bond between the oxygen and the carbon, and that's going to be approximately 96 picometers in length. And so these bonding forces that we see in the covalent or ionic bonds, those happen at very close distances, whereas the intermolecular forces we're talking about right now are going to be a lot weaker because the distances are much bigger. This is 3 times the distance, right? So the intermolecular force attracting 2 molecules to each other. So the first type of force we'll talk about is called a dispersion force. It also has some other names, sometimes called London forces or London dispersion forces or induced dipoles. I'll try to call them dispersion forces because that's what the book calls them. This type of force is present between all particles, all molecules, all atoms. And it's a result of fluctuations in the electron distribution. So if we look at this picture of helium, right, we've got 2 electrons. And remember, electrons are particles and waves at the same time, right? But if you snap a picture of them, they have to behave as a particle and you could see where it is, right? So we're taking a picture here, there's one over here and one over here. The next time we take a picture, they're kind of on opposite sides. In the third picture, we happen to catch both of those electrons on one side of the atom. When they are both on this side, they have the negative charge, the nucleus has the positive charge. This has become a little bit unbalanced, right? This side of that atom is going to have a partial negative charge. This side is a partial positive charge. This Greek letter delta, it's a lowercase delta, looks like kind of a slouching D, right? That means a partial charge. So this is not a -1 and a +1 charge. This might be a -0.1 charge, and a plus 0.1 charge. These are small charges. But at any given instant, the electrons in an atom or molecule can be unevenly distributed. Does anybody have any questions about that? You can think of the electrons as just, sort of randomly being around, and they're independent of each other. And so at any given time, they could all end up on one side. Most of the time, they're going to be more spread out, but they could end up on one side, right? So an instantaneous or a temporary dipole happens when we have an interaction between one atom or molecule that is temporarily lopsided and a neighboring molecule. So this one just happened to be lopsided, and then the positive end of that atom is going to attract the electrons of a neighboring atom and cause this one to also be lopsided. And then that one's going to have an effect on this one. And so this is why they're sometimes called induced dipoles, because one happens by chance, and then that causes dipoles in neighboring atoms. And then there is a force of attraction. This force of attraction between the separate atoms or molecules is the dispersion force. It's very weak. Any questions? The size of that force, the magnitude of it, will depend on how easily the electrons can move. How easily can this atom or molecule get lopsided, right? Have this spontaneous charge imbalance, and how easily influenced is it by other atoms, right? So what we find is that a larger electron cloud is going to be easier to polarize because the electrons are held less tightly by the nucleus, whereas a smaller one is less easy to polarize. So I think of this in terms of like a large and a small family. You get a small family, 2 kids, like helium has 2 electrons. It's easy to keep track of them, right? Keep them on task, whatever. You get 6 kids, or heaven forbid, like xenon, 54, right? And they're spread around. They're further away from you, right? And you can't possibly keep up with all of them. And so could you end up with a bunch of them on one side? Yeah, very easily. So it reminds me of the time I walked into the living room and I saw all 6 of my kids sitting on half of the couch. I took a picture. They were looking at something. And it was just like, because that almost never happens, right? But it can. What made them do that? Well, they were all interested in this thing that we're looking at. I don't know if it was a cell phone or a book or something, but they were all pulled by that. They were attracted. And so that's what happens. You get an instantaneous dipole in one atom, and it draws the cloud of a neighboring atom. So the larger the atom, the easier this can happen, and the larger the charge difference. And so we see that as we get larger, the boiling points are going to go up. So the boiling point of helium is 4.2 Kelvin. Xenon is 165. The boiling point is a measure of how strong the intermolecular forces are. Because in order for a liquid to boil, the particles have to have enough kinetic energy to escape from those forces that are holding them together, right? If those forces are very weak, then it will boil at a lower temperature. So this tells us that the intermolecular forces, the dispersion forces in helium, are much weaker than in xenon. So we can see that dispersion force strength generally increases with molar mass, with size. The shape of a molecule also plays a part. So this is N-pentane and this is neopentane. They have exactly the same chemical formula, same number of carbon and hydrogen atoms. What's different is how they're connected to each other. So their molar masses are the same, but one boils at 36 Celsius and one boils at 9.5. That tells us that this one the intermolecular forces holding it together are weaker. And we can understand that by looking at the shape. This one is more long and skinny, kind of a cylinder shape. And so these two molecules can interact across this area here. In order for the dispersion force to act, you have to be able to get close to the other one, right? And so here we've got this whole side is able to get close to that one. Whereas with the neopentane is more spherically shaped, and so no matter how you try to arrange these guys, you can only get close in one small area. And so the forces of attraction here are going to be lower, and that's reflected in the lower boiling point. This is just looking at how the boiling point changes with molar mass. These are all just carbon-hydrogen hydrocarbons, and these are all of the same shape, right? They're all the long, skinny kind. But we see that as the molar mass increases, as the size increases, the boiling point goes up. So you could be asked a question like C5H12 and C9H20, which has the higher boiling point? Well, the larger molecule is more easily polarized, it's going to have stronger dispersion forces. So that will have the higher boiling point. Yep, got ahead of myself again. So here, which of these halogens has the highest boiling point? What are we looking for? We're looking for which one's the biggest, right? And iodine is the biggest. How do we know that? Well, periodic trends, it's at the bottom of this column. It goes chlorine, bromine, iodine. Size gets bigger as you go down. You can also just look at the molar mass, right? Molar mass of 126 versus 35, it's a lot bigger. Okay. The second type of force is called the dipole-dipole force. This is present in polar molecules. It is not present in nonpolar molecules. This is stronger than a dispersion force, and that's because these are attractions between permanent dipoles. This isn't just an instantaneous dipole that was there for a second and then it's gone and then later it comes back again. You've got that spotty, just every once in a while attraction. Here, the dipole is always there, and so there's always this force of attraction. Here, looking at a space-filling model of a polar molecule. This side of the molecule has a partial negative charge, and this side has a partial positive charge. The negative end of this one is attracted to the positive end of the other one. And so, that force is going to be stronger than dispersion forces. Remember that dispersion, everything has dispersion forces. So the polar molecules have dipole-dipole forces and dispersion forces. So we'll see that polar molecules have higher melting and boiling points than nonpolar molecules. And we have to just compare one difference at a time. We don't want to be looking at different masses and different polarities. So here we're looking at two compounds that have very similar molar masses, right? I mean, it's hard to get closer than that. This one here, we should be able to identify as polar. My rules for good enough are, look at the central atom. If there's no lone pair and all the atoms bonded to it are the same or have the same electronegativity, it's nonpolar. Well, here we have no lone pair, but one of these is very different than the others. The oxygen's different than the hydrogens. So we should predict that that's polar, and in fact it is. This one, just carbons and hydrogens, I told you need to remember that a carbon-hydrogen bond is a nonpolar bond. That's the only one that you need to remember. Otherwise, if you see a bond between two different elements, you should assume that it's polar, because that works most of the time. But this is important. This is all non-polar bonds, so there's no way that this can be polar. So we see here that this has a boiling point of negative 19. This has a boiling point of negative 88. So this boils at a much lower temperature. It takes less energy to break ethane molecules away from each other because they're not so attracted to each other. And this is another graph just showing how the boiling point increases as you increase the polarity. Acetonitrile is more polar than propane. These all have very similar molar masses, so the boiling point goes up as the molecule becomes more polar. Polarity is also important in determining miscibility. So that might be a new word. It sounds like mixability, which is not a word, but if we say it, you know what I mean, right? Mixability, the ability for it to mix. Miscibility is the ability of two liquids to mix together in any ratio. One saying that we have that helps us to identify whether things might be soluble or not, or might be mixable, miscible or not, is like dissolves like. So here, if we take oil and water, well, not oil, sorry, but propane, pentane and water, and mix them together, the water molecules are polar. They have dispersion forces and dipole-dipole forces, right? C5H12, all carbon-hydrogen bonds, nonpolar. It only has dispersion forces. So we can think of those intermolecular forces almost as being like a language that allows the molecules to be attracted to each other. So if you think about, okay, so all my ancestors came from Sweden, all of my husband's ancestors came from Japan, so I'm going to talk about Japanese people and Swedish people, and you can't accuse me of anything, right? So we've got a room full of a bunch of Japanese people who don't speak English and a bunch of Swedish people that don't speak English. Those are actually really hard to find, but both those countries speak English a lot. Anyway, are the Swedish people and the Japanese people going to be getting together and having conversations and be attracted to each other? No, they're not, right? What's going to happen? You're going to have a little group of Swedish people here, a little group of Japanese people talking in Japanese, right? And they're just going to clump up with other people that speak their language, right? Like is attracted to like. It's hard to interact with someone when you don't have any language in common. And so that's what these two things are like. One is speaking dispersion forces, the other is speaking dipole-dipole forces. Right? And so they're not going to interact. If they both had dipole-dipole forces, or they both only had dispersion forces, then we would predict that they would mix together. Okay, so which of these molecules has dipole-dipole forces? What are we looking for? What kind of molecules have dipole-dipole forces? Polar molecules. Well, just looking at these formulas, it's not really obvious which ones are polar, right? So we really need to look at the Lewis structures. So carbon tetraiodide is going to be a carbon and have 4 iodines around it. And then these guys are going to have lone pairs. And we could find out the electron geometry and the molecular geometry and look at how the polar bond vectors are adding together, but we're not going to do that. We're going to use my little rule of thumb. Are there any lone pairs on the central atom? No. Are all of these guys the same? Yes. This is a nonpolar molecule. Nonpolar molecules are very symmetrical. They don't have one end that's different than another. So this one is nonpolar. Is it going to have dipole-dipole forces? Wait, CH3Cl. What do you think about that one? Polar or nonpolar? Yeah, this one's going to be polar. There are no lone pairs here, but one of these is different, right? So this has a different electronegativity than the hydrogens, and so this molecule is going to be lopsided. It's going to be polar. So will that have dipole-dipole forces? Yeah, it will. What about HCl? HCl is a very simple molecule. It's just got two atoms, right? So then we can't use this central atom business because there's no central atom. But there's only one bond. Is this a polar bond? So what I expect from you, without looking at electronegativity values and stuff, if these are two different elements, I expect you to tell me it's polar. There are certainly places where that's not correct, but I'm not going to give you any of those on an exam, and they don't come up very often anyway. So these are different elements, so I expect you to predict that this is polar, and it is polar. So will that have dipole-dipole forces? Yeah. So this carbon-hydrogen bond, that's the one exception I want you to remember. Carbon-hydrogen bonds are considered nonpolar. Any questions? So here we have an electrostatic potential map for this molecule acetonitrile. It's polar. And so the red over here is showing that there's more electron density here and there's less electron density over there. So from the map, determine the geometry for how two acetonitrile molecules would interact with each other. Which of these orientations is most likely? How are they going to be attracted to each other? Well, that's all kind of confusing. Let's think about this without looking at that first. So this is our negative end of the molecule, and this is our positive end of the molecule, right? What is this going to be attracted to on another acetonitrile molecule? The positive end. So the positive end, the negative end of this is going to be associated with the positive end of the other one. So now let's look at these guys. So this is the nitrogen. So here we have the nitrogen end close to the non-nitrogen end, right? So that looks like a good candidate. Here we have the negative ends sort of being next to each other. That's not going to be very attractive. Here we have the negative end aiming at the side of the molecule. And here we have the two negative ends head on with each other. So this is like two magnets. You're trying to push the two north poles of the magnet together or the two south poles. These are like charges. Both of these are a little bit negative, and so they're going to repel each other. The way they're going to stick together really well is if you get the negative end and the positive end close to each other. Next type of intermolecular force is called hydrogen bonding. And we can think of this as being super dipole-dipole force, right? There's dipole-dipole force, and then there's super dipole-dipole force. So this, like other dipole-dipole forces, is found in polar molecules, but these have something a little extra. Oops. Got all lost in my slides. Okay. These have a hydrogen that is covalently bonded to fluorine, oxygen, or nitrogen. These are the special ones because they are very small and they're very electronegative. And so they allow the neighboring molecule to get in close to a larger charge. Well, how do you remember this? Have you seen the movie E.T.? Very old movie. Please. Okay. What did E.T. say a lot? He pointed at the sky and said, E.T., phone home. Phone home. Phone home. Maybe it's a little bit of a stretch, but, got to do something. So for hydrogen bonding, we need one of these guys bonded to hydrogen. Here we have, we're looking at an HF molecule, and so here's the fluorine. It's very electronegative. Hydrogen is not very electronegative, and so the dipoles in these molecules are extra strong. And this guy is also small relative to some of the other elements, and so these guys can get closer together. So let's look at hydrogen bonding in a couple of compounds. Let's start with water. So water molecules, if we don't show the lone pairs on the central atom, then we may forget that they are polar. But each of these oxygens has 2 lone pairs, and so there's my criteria. Does it have lone pairs on the central atom? Yes, it's polar. So this is a polar molecule. Does it have phone home? Yes, it has oxygen bonded to hydrogen. So the positive end, the hydrogen ends of these molecules will be attracted to the oxygen ends of neighboring molecules. And this dashed line here, this red thing, that is the hydrogen bond. The black line between H and O, I know it's a bond between oxygen and hydrogen, but that's not a hydrogen bond. Okay, the hydrogen bond is an intermolecular force between molecules. Here's another polar molecule, and even without looking at its Lewis structure, here we have oxygen, and over here we have carbons and hydrogens. All of these carbon-hydrogen bonds are nonpolar, and then we throw this oxygen that's different in there, and this is lopsided. It's not a symmetrical molecule. So this is polar, and it has that oxygen-hydrogen bond. So again, we're going to get attraction between the oxygen part and the hydrogen part of neighboring molecules. So again, hydrogen bonds are between molecules. Chemical bonds are between atoms within a molecule. So this actually kind of belongs up here maybe. The hydrogen bond is only at most 5% as strong as a covalent bond. These are much, much weaker than covalent bonds. But we see that they do have a big effect. So here we can compare ethanol with dimethyl ether, same chemical formula, so same molar mass. Which one of these looks lopsided? Or more lopsided? This one, right? This one has an oxygen in it, and so it is a little bit polar because this side is negative and that side is positive. But over here, we also have a polar molecule, and this has the oxygen-hydrogen bond. This one has oxygen-carbon bonds and hydrogen-carbon bonds. So we don't have phone home happening there. So this is a polar molecule without hydrogen bonding. This has hydrogen bonding. And so when we look at the boiling point, ethanol boils at plus 78 degrees Celsius, and dimethyl ether boils at negative 22. The forces of attraction between these molecules are much weaker than those between ethanol molecules. So water has hydrogen bonding because it's polar and it has that hydrogen-oxygen bond that satisfies our phone home business. So if we predicted what should happen, is that, this looks kind of linear, right? And then that one is way up there. What we're looking at here is molar mass and boiling point for compounds with hydrogen. So these are the group 6A elements. We've got tellurium, selenium, sulfur, and oxygen. These are all going to be polar molecules because they have lone pairs on the central atom. And then here we have some nonpolar molecules with the group 4A. And so these boiling points are lower than those because these are nonpolar. So these are higher, but then what's going on with water? Why is its boiling point so much higher than we would expect? Because water is the only one of these compounds that has hydrogen bonding holding it together. So without hydrogen bonding, the boiling point of water would be close to, maybe negative 90 degrees Celsius, which means that all water would be a gas at room temperature. That would affect life as we know it, wouldn't it? Okay, this is a kind of question you should be able to answer for like a test. Which has the higher boiling point, HF or HCl? I hear little whispers of HF. That's correct. HF. Why? ET phone home, right? So here we have two diatomic molecules. There's just two atoms. There's just one bond. Both of these have polar bonds because it's between two different elements, right? So both of these are polar, but this one has a hydrogen-fluorine bond, so this can engage in hydrogen bonding. This does not have hydrogen bonded to fluorine, oxygen, or nitrogen. There's no phone home going on here, okay? So stronger intermolecular forces, higher boiling point. The last one is called an ion dipole force, and I would argue that this is not an intermolecular force because it's not between molecules. It's between molecules and ions. But this is an important force. So ion dipole force is the interaction between the dipole of a polar molecule and an ion. This is a big part of how substances dissolve in water. And this attraction is stronger even than hydrogen bonding because here, this is an actual ion with a full -1 charge. And even though water engages in hydrogen bonding and this is a fairly high positive partial charge, it's nowhere close to +1. And so these guys interacting with each other, that hydrogen bonding is weaker than this force of attraction. So water has a positive side and a negative side, right? So the positive side of water is attracted to negative ions, but if there's a positive ion, the water can just turn around and show the negative side to the positive ion, and there's attraction here. And so I sometimes think of, what happens when sodium chloride dissolves in water? Well, the solid, you've got sodium and chloride ions, and they're stuck to each other, right? They're very attracted to each other. Well, how do you get them to separate? Well, here's chlorine, and chlorine's going to get surrounded by a bunch of water molecules that are going to be all nicey nice to it, right? Oh, we like you, right? And so it's like, well, these guys are really nice. I mean, that guy was really nice too, but look at all of these guys. And so they're kind of lure it away, right? And the sodium can also get lured away by the water because the water's two-faced, right? It's got two different sides, and it's going to show the side that's attracted to that ion. And so this sodium ion also can get its interactions with chlorine replaced by interactions with several water molecules. This just summarizes the different types of intermolecular forces. Understanding the trend in the strength here is important. Dispersion forces are the weakest. Next is dipole-dipole. Hydrogen bonding is the next strongest, and ion dipole forces. What's important here that is explained here with the asterisk, the dispersion force can be very strong if we're comparing things with different sizes, right? So if you're trying to compare something based on type of intermolecular force, you need to have the size of the thing be similar, right? Because if you get like fat molecules, well, fat molecules are nonpolar. Why are they a liquid or even a solid at room temperature? Because they're very large. And so even though they only have dispersion forces, their dispersion forces may be larger than hydrogen bonding in water, and the boiling point might be higher. So this trend is helpful when you're comparing molecules of similar sizes. So which of these substances has the highest boiling point? And if you compare the molar masses of these, you'll find that they're in the same ballpark. So high boiling point, are we looking for strong intermolecular forces or weak? Strong. So we want to find the strongest force. So the strongest force, here there's no water involved, so we can't have the ion dipole. So we're looking for, do any of these have hydrogen bonding? Well, this can't have hydrogen bonding. It doesn't have any hydrogen. And this one can't either. What about this one? Well, phone home. Yep, we've got oxygen-hydrogen bond. So we should predict that this substance has a higher boiling point, and it does. This is methanol, which is a liquid at room temperature. Carbon monoxide is a gas. Nitrogen is a gas. Most of the air we're breathing in is nitrogen. Hydrogen bonding is very important in biological systems. Here's an example, your DNA. So DNA is composed of two strands that are held together by hydrogen bonding. And your body can replicate DNA by by separating the two strands of the original DNA and then creating a new strand that matches one of these old strands and will match up over here. And so it's going to take these bases and they're going to attach here based on what's over here. So we see that thymine and adenine are always going to be complementary to each other, cytosine and guanine. And the reason is that these two will make 2 hydrogen bonds, and these two will make 3 hydrogen bonds. So here's a cytosine. What's going to come in here and attach to that? Well, it's going to be a guanine. So these guys come in here, and then that phosphate backbone forms, and you make new DNA.